Okay, in this section, we are going to talk about what are called fundamental identities of trigonometric functions. Okay? This area is called analytical trigonometry, where we analyze different trigonometric functions. Okay, and use different methods to analyze trigonometric functions. And identities means two things are equal to each other. So we're going to try to take some form of a trigonometric equation and simplify it to another trigonometric equation. That's called an identity. So normally we take something that's complex and simplify it to something simple. And we're going to learn how to do that. So that's what we call evaluating trigonometric functions and simplifying them. We're going to look at how to create these identities and then solve some trigonometric equations using these identities. That graphic has nothing to do with anything. All right, some of these we already talked about a little bit earlier in the course. We have our reciprocal identities. We know that cosecant is the reciprocal of sine. Sine is the reciprocal of cosecant and so forth. Quotient identities, we know that tangent is y over x or sine over cosine. And cotangent is the reciprocal of that. We talked about cofunction identities, the angles within a right triangle. If I have a right triangle, and if this is angle theta, this angle up here is going to be pi over 2 minus theta. So sine of this angle is equal to cosine of this angle. Cosine of this angle is equal to sine of that angle. And there's the other ones there. Okay. I'm going to give you these trig functions. You don't have to memorize them, but you are going to have to know how to use them. We talked about negative identities in a previous lesson. And we're not going to use those too much, but keep those handy, all right? And also, most important one here, the Pythagorean identities. The one that we're going to use the most is sine squared theta plus cosine squared theta is equal to 1. So any place that I can come up with that, I can reduce my expression to 1, which makes things a lot simpler than sine squared plus cosine squared. So let's take a look at the Pythagorean identity here of sine squared plus cosine squared equals 1. So if I have sine squared theta plus cosine squared theta is equal to 1, here they use u. I don't know why. It could be anything. Sine squared u is equal to 1 minus cosine squared u. Or cosine squared u is equal to 1 minus sine squared u, just rewriting the identity. And from our other ones there, we could keep these handy as well. We're not going to use these too much, but just from the previous page, we're going to have all these available to us to simplify things. We're not going to use this one too much either, but we could if we wanted to. That I could take the square root of this. The square root of sine squared is equal to sine is equal to plus or minus the square root of 1 minus cosine squared u. And same thing with tangent, okay? And then depends on which quadrant you're in. Remember, sine is positive in quadrants 1 and 2, and negative in quadrants 3 and 4. Tangent is positive in quadrants 1 and 3, and negative in quadrants 2 and 4. So it just depends on which quadrant you're in. One common application of trigonometric identities is to evaluate other trigonometric functions and try to simplify them. Okay, we learned this earlier by drawing triangles, and then this is simply another way of doing that, and hopefully help us understand what we're going to be doing in the next couple of sections. So let's take a look at an example here. Use the value secant equals -3/2, and tangent is greater than 0 to find all 6 trigonometric functions. So if I use my reciprocal identity, I know that secant is the reciprocal of cosine. So cosine is going to be 1/-3/2 or -2/3, just flipping it over. Now that we have cosine, we can use the Pythagorean identities to find sine. This is another way. We could have done it with drawing a triangle, but this is another way to do it. So if sine squared plus cosine squared is equal to 1, then cosine squared is equal to 1 minus sine squared, or sine squared is equal to 1 minus cosine squared. So my sine squared is going to be equal to 1 minus cosine squared, -2/3 squared, is equal to 1 minus 4/9 equals 5/9. So sine is going to be the square root of that, which turns out to be the square root of 5/3, plus or minus. But we know that tangent is greater than 0, and secant or cosine were less than 0. That must mean we're in quadrant 3. So sine will be negative in quadrant 3. So we're going to use the negative square root for sine. So this is another way of doing what we did with triangles in last chapter. We're not going to be doing too much of this, a little bit, but. And now that we know the values of sine and cosine, we can find the other ones here. So tangent is sine divided by cosine using a quotient identity. Turns out to be square root of 5/2. And then we can just use the other reciprocals to find the other one. So this is a little bit more complicated than just drawing a triangle, but it's just to show you that these identities work, that we can do them. All right, let's take a look at the guided practice here. Let me find it. I'll do that over here. So under chapter unit 4, analytical trigonometry, we're in chapter 5. We've got the Moodle page here, and then I'm going to go to the chapter 5 tab. And under chapter 5 tab, you will find the in-class worksheet, and you'll also find the in-class worksheet answer key. Let's make this a little bit larger. Let's just look at numbers 1 and 2 here. This is a little bit cumbersome, so I'm going to go through it. It says use the given values to find the values of all 6 trigonometric functions. I've got tangent of theta is equal to 2, and sine is less than 0. So that must mean if tangent is positive and sine is negative, we must be in quadrant 3. Okay, ASTC, so T is positive in quadrant 3. So the first one's easy. Just take the reciprocal of tangent to give us cotangent. So cotangent is equal to 1/2. That's easy. Now I'm going to use a Pythagorean identity here to find secant. So 1 plus tangent squared equals secant squared. So I took that from the list of identities. Again, you're going to have those lists of identities, but you're going to have to know how to use them, right? So tangent squared is, tangent is 2, so 2 squared is 4, plus 1 is 5. So secant squared is equal to 5. So secant is equal to plus or minus the square root of 5. But since we're in quadrant 3, cosine would be negative. So cosine is going to be the reciprocal of secant. Negative 1 over the square root of 5. And now that I have cotangent, I can use cosecant squared plus 1 plus is equal to 1 plus cotangent squared. Again, this is kind of the hard way to do it, but it's showing you that these trigonometric identities work. Cosecant squared is equal to 1 plus 1/2 squared. So that equals 5/4. 1 plus 1/4 is 5/4. So cosecant is going to be the square root of that. And again, sine is negative in quadrant 3. So there's my other 5 trigonometric functions. All right, number 2, sine is equal to the reciprocal of cosecant. So sine is easy. Sine is equal to negative 1/5. It looks like it's hard to see the negative there. Then I can use my Pythagorean identity. Cosine squared is equal to 1 minus sine squared. Well, if sine squared is 1/5 and cosine squared is 1 minus negative 1/5 squared, 1/5 squared or negative 1/5 squared is 1/25. So cosine is equal to, cosine squared is equal to 24/25, or cosine is equal to the square root of that. So cosine is equal to the square root of 24 over, or negative square root of 24 over 5. Square root of 24 we can reduce to 2√6. Square root of 25 is 5. Again, we are in quadrant. If cosecant is negative and cosine is negative, this is also in quadrant 3. I probably didn't say that yet. This is in quadrant 3. So secant is going to be the reciprocal of cosine. And then tangent is sine divided by cosine. So negative 1/5 divided by negative 2√6 over 5. The 5's cancel out, the negatives cancel out, and I'm left with tangent is equal to 1 over 2√6. Cotangent is the reciprocal of that. Cotangent is equal to 2√6. So again, it probably would have been easier to do with triangles and just draw a triangle, but this is showing you that the trig identities do indeed work. All right, so what good is it to use these trigonometric identities? When factoring trigonometric expressions, it is helpful to find a special polynomial factoring form that fits the expression. Okay, we're not going to do too much of this either. On occasion, factoring or simplifying can best be done by first rewriting the expression in terms of just one trigonometric function or in terms of sine and cosine only. Let's take a look at an example here. I'm going to kind of treat this like a polynomial. I've got this expression sine x times cosine squared x minus sine x. The first thing I notice is that I can factor out a sine x. So the first thing to do would be just as just like in a polynomial, we can factor out a common term. Well, here we can factor out the common term of sine, and we're left with sine x times cosine squared x minus 1. So here I'm going to factor out a -1 and flip this around so it becomes 1 minus cosine squared x. The reason I did that and factored out the minus is because now I have a Pythagorean identity. 1 minus cosine squared x is equal to sine squared x. Sine squared x times negative sine x is negative sine cubed x. So we took the original expression and simplified it down to one term. And that's kind of the purpose of what we're doing here, trying to simplify these into the simplest possible form. Now, when we're doing these, I'm going to say this more than once, is if they start to get more complicated, then we're probably going down the wrong path. So it always should maybe get a little bit more complicated, but then it should simplify out afterwards. But if it just keeps getting more and more complex, probably stop, try something else. So don't spend hours and hours trying to simplify it if it just keeps getting huger, okay? It probably means that there's a better path to take. So here's a couple of ones that we can simplify. This one's pretty easy. Here I've got cotangent of u is equal to, thank you. Cotangent u times tangent u. Well, this is pretty simple. There's more than one way to do these, but this was probably the simplest way. Just write cotangent as cosine u over sine u, tangent as sine u over cosine u. Those two terms just cancel each other out, and we're simply left with 1. So that's pretty nice. Let's take a look at another one. Here I've got secant u times sine of u. Well, I don't like secants and cosecants. If I don't have to use them, I'm going to change them to a cosine or a sine. And secant happens to be 1 over cosine. So I have 1 over cosine times sine of u over 1. Well, that equals sine u over cosine. That does not equal 1. That equals this tangent. I don't know how I got the, hang on, let me fix that right now. Know how that got in there. All right. So sine u over cosine u is equal to tangent. Hopefully it'll show up here in a second. So secant u times sine u, we can simplify to tangent of u. Let's try one that's a little trickier here. Here I've got secant squared u minus tangent squared u. Well, there's a number of ways we can do this. Okay, we could use trig identities maybe to substitute for tangent squared or secant squared. But usually the first way I do it is translate things to sine and cosine. So what do I have here? I've got 1 over cosine squared u, that's my secant squared, and tangent squared I can express as sine squared over cosine squared. Then I've got a common denominator, so I can combine the numerators, 1 minus sine squared u over cosine squared u. 1 minus sine squared u. Well, that's equal to cosine squared u. Yes, yeah. Over cosine squared u is simply equal to 1. So I can take that first expression and I can simplify it down to 1. So that's pretty much our goal here with these expressions, is try to simplify them. And again, if they get more complex, then we're probably going down the wrong path. All right, let's take a look at the in-class worksheet over here. 3 through 6. Try to match the trig expressions to one of the following by simplifying it. Well, cotangent squared x minus cosecant squared x. Using my trig identity for cosecant, I can replace that with 1 plus cotangent squared. The reason I did that is because now cotangent squared minus cotangent squared cancels out, and I'm left with -1. So that's B. 4 sine of -x over cosine of -x from my negative identities. And again, I'm going to give you a sheet with all those on there. There's one out there already under chapter 5 at the very bottom. There's a cheat sheet. It's going to have all these. What's that?
Zoom in a little bit, just a tiny bit.
So this one, sine of -x is equal to negative sine of x. Cosine of -x is equal to cosine of x. And then negative sine of x divided by positive cosine of x equals negative tangent of x. Again, there's more than one way to do these. Okay. There's more than one way to do these. Number 5, sine of x times secant of x. I think this is one we already had. Secant I can express as 1 over cosine. Sine divided by cosine is equal to tangent. Number 6 is a little bit tricky. I've got secant to the 4th x minus tangent to the 4th x. I'm not going to have one quite this tough on the test or anything, but just showing you how it works. Secant squared x squared minus tangent to the 4th. We'll just deal with that later. 1 plus tangent squared x squared. So I did a Pythagorean substitution here. And now I have 1 plus 2 times tangent squared x, just foiling this thing out, plus tangent to the 4th x minus tangent to the 4th x. So these two cancel each other out. And I'm left with 1 plus 2 tangent squared x. Well, I'm going to expand that out to 1 plus tangent squared plus another tangent squared so that I can combine this using Pythagorean identity. So like I said, don't worry, I'm not going to have one this complicated on any test or quiz. Yes, yeah. But just showing you how these things can work, all right? So 1 plus tangent squared x, I can combine that into secant squared x plus tangent squared x. So I took the original, which was up to the 4th power, and I reduced it to something that was the 2nd power. So it's a little bit simpler. And there's probably more than one way to do this one too. So don't think that there's only one way to do these, okay? I've said that many times in math. Sometimes there's more than one way to do these. All right. And again, this answer sheet is out there. So when we need to simplify a trig expression, okay, check the identities that we know from our sheet and look for similarities. If the function is squared, look for Pythagorean identities that we can substitute. If you have tangent or cotangent, look at the quotient identities that we've used. And if you have secant or cosecant, look at reciprocal identities. Try to turn it into a sine and cosine. It makes it easier. So if it's not obvious, then try to change everything to sine or cosine. Those are usually the easiest ones to work with. Try to cancel things out. Try to gather like terms. Okay? And I don't like this method, but some people use X for cosine, Y for sine. That's kind of substituting back what we did before. I like to keep things as sine and cosine so I can see it. Right. So let's take a look at this one. Here I've got sine t plus cotangent t times cosine t. Well, I've got a sine and a cosine, and then I've got this cotangent in the middle. Let's convert that to sine and cosine, and maybe things will simplify. So if I've got cotangent and I convert that to cosine over sine, now my expression is sine t plus cosine t over sine t times cosine t. Well, I don't know if that's making it simpler or not, but again, sometimes these get a little bit more complicated and then they should get simpler, all right? So this is kind of a graph I like to use. When I'm solving these, they start to get a little bit more complex, but then they should get simpler. If it starts getting more and more complex and just keeps going more and more complex, then stop, try a different path. So we'll try this path and see where it takes us. Well, now I have I want to get a common denominator of sine. So how am I going to do that? I'm going to multiply the first term by sine over sine. Okay, I can do that. That's just 1. So I can multiply the first term by 1. And what am I left with? I'm left with now sine times sine, which is sine squared t, over my common denominator of sine t. And here I've got cosine times cosine squared over sine t. So again, it's a little bit more complicated, but I think I see what's going to happen. I've got a common denominator of sine here. So now I have sine squared t plus cosine squared t over 1. And now I know from my Pythagorean identities, sine squared plus cosine squared is equal to 1. Okay, you're going to want to remember that. So I've got 1 over sine t, which I can reduce to cosecant of t. So I took that original expression and I simplified it down to 1 term. All right, let's take a look at number 7 and 8 now. Factor the expression and simplify this one. I've got sine squared times secant squared minus sine squared x. Now the first thing I see is that I've got a common factor of sine squared. So let's factor that out. Now I've got sine squared x times secant squared x minus 1. Well, looking at my Pythagorean identities. So again, keep that sheet of identities handy. That's equal to tangent squared. Now, there's not a whole lot I can do with that. I could simplify it a little bit more, maybe by breaking tangent into sine squared over cosine squared, but that's about as simple as we can get it. All right, this one, I've got cosecant cubed minus cosecant squared minus cosecant x plus 1. Again, I wouldn't do anything, hopefully, this tricky to you on a test. But I can factor out a cosecant out of the first two terms here, or I rewrote it so that I put this term over here and this term over here. So I've got cosecant cubed minus cosecant x minus cosecant squared plus 1. The reason I did that, and again, this is kind of tricky, is that now I can factor out one of the cosecants here. And I've got a common term here of cosecant squared x minus 1 minus cosecant squared x minus 1, because I factored out of minus 1 out of this. Using my trig identities, that's equal to cotangent squared x. So now I can factor, and this is also cotangent squared x. I can factor out a cotangent squared x. And I'm left with cotangent squared x, and my term that's left is cosecant minus 1. So I take something that was in the third power, reduce it to the second power. That's about as best as I can do. All right, again, I wouldn't do one that tricky to you on a test or anything. Yeah, yeah.
This is just like
Yeah, we're just trying to simplify things. Just trying to simplify things. All right. When we're trying to factor these, sometimes people like to treat them like polynomial expressions, and you could do that. That doesn't work. Try changing things to sine and cosine. Try the other Pythagorean identities. So let's take a look at an example here. Here I've got secant squared theta minus 1. Well, if I wanted to, I could treat this like a difference of squares. A squared minus b squared is equal to a minus b times a plus b. So I could reduce that to secant theta minus 1, secant theta plus 1. Not much more I can do with that. Okay. This one over here, if I wanted to, I could treat it like a polynomial, substituting u for tangent. And I've got 4u squared plus u minus 3, and I could factor that like a polynomial then. 4u minus 3 times u plus 1. Okay, I'm not going to go into factoring right now, but and then just substitute back in for tangent. All right. So let's take a look at another example. Here I've got cosecant squared x minus cotangent x minus 3. So I think the first thing I'm going to do is substitute in for cosecant x, my Pythagorean identity, which is cotangent squared x plus 1. So now I've got cotangent squared x plus 1 minus cotangent minus 3. So minus 3 plus 1 is a minus 2. And now I can factor this like a polynomial if I wanted to. U squared minus u minus 2 is equal to u minus 2 times u plus 1. And substituting back in cotangent x minus 2. Substituting back in cotangent for u, cotangent plus 1. So this is just showing you that we can treat these like polynomials if we wanted to. All right, the next example shows adding these functions together and how we can maybe do that. So here I've got this somewhat complicated expression and I want to simplify it. I think the easiest way to do it is to find a common denominator. So that means multiplying the first term, top and bottom, by the denominator of the second, and take the second term, multiply top and bottom by the denominator of the first. So what is that going to look like? So I'm going to multiply the first times sine over sine. And I'm going to multiply the second times 1 plus cosine over 1 plus cosine. Just like we did back in algebra, trying to find a common denominator. So now I can multiply sine times sine gives me sine squared. Cosine times 1 gives me cosine. Cosine times cosine gives me cosine squared. And my common denominator is sine times 1 plus cosine. So it gets a little bit more complicated in the middle here. Okay. So I'm going to rewrite this as sine squared plus cosine, just switch these two terms, because now I have a Pythagorean identity there. Well, that's nice, because that turns out to be just 1. So now I've got 1 plus cosine of theta, and that's going to cancel out with the 1 plus cosine of theta in the denominator. And I'm left with simply 1 over sine, which is equal to cosecant. So these are a little bit tricky, and they get to be a little bit frustrating once in a while, I'll be honest. But the more you try them, the more you do them, the more you'll start to see patterns of how to do these. So again, if you see squares and stuff, look for Pythagorean identities. Sine and cosine are usually the easiest to deal with. Look for things you can cancel out. Okay. All right, let's jump over to 9 through 13 now. I lost it. Where to go? All right, number 9, sine plus cosine squared. It's not 1 because it's not sine squared plus cosine squared. I have to FOIL this thing out. I've got sine squared plus 2 times sine times cosine plus cosine squared. Well, now I've got a sine squared plus cosine squared, and that is equal to 1. But I still have this other term, 1 plus 2 sine x cosine x. Not much more I can do to simplify that. All right, let's take a look at this one over here. This is a little tricky. It's kind of like the one we did before. I'm going to find a common denominator here, and that's going to be 1 plus sine, but I want to change my tangent to sine over cosine, because now I've got everything in sine and cosine. Again, there's more than one way to do these. I don't know if this is the easiest way or not. So don't be afraid to try different ways, okay? Just because I did it one way doesn't mean it's the only way. So I'm going to multiply top and bottom of the first by 1 plus sine of x, the denominator of the second. I changed this to sine over cosine, so I'm going to multiply the second by cosine over cosine. And this is similar to the one we did on the board over there, or on the PowerPoint before. 1 times sine is sine of x, sine times sine is sine squared, cosine times cosine is cosine squared, and then my common denominator is 1 plus sine x times cosine x. Well, sine squared x plus cosine squared x is 1. So I've got 1 plus sine of x, which is going to cancel out with this 1 plus sine x in the denominator. I'm simply left with 1 over cosine x, which is equal to secant of x. So that one canceled out real nicely. This one says use the trig substitution to write the algebraic expression as a trig function. So 9 minus x squared, take the square root of that. And I've got x is equal to 3 times cosine of theta. Well, if 3 cosine theta squared is 9 minus 9 times cosine squared, I can factor out a 9, and I'm left with 9 times 1 minus cosine squared, which is equal to the square root of 9 times sine squared, because 1 minus cosine squared is sine squared. Take the square root of that, and I've got 3 sine of theta. I suppose that should be plus or minus. No, it's just the square root, so it's just positive square root. This one's similar, x squared minus 9. Take the square root of that. If x is equal to 3 secant of x, so I've got 3 secant x theta squared. So that becomes 9 secant squared theta minus 9. I can factor out the 9. And I'm left with 9 times secant squared minus 1. Using my trig identities, my Pythagorean identity. Secant squared minus 1 is equal to tangent squared. Take the square root of 9 tangent squared is equal to 3 tangent theta. All right, number 13 is, now I've got an expression here, equation, and I want to solve for theta here. So I've got 2 root 2 is equal to square root of 16 minus 4 x squared, where x is 2 cosine of theta. So this is similar to what we were doing before. So I've got, I'm just going to leave the 2 root 2 on the left side. I'm going to simplify this. 16 minus 16 cosine squared, factor out the 16. Square root of 16 times 1 minus cosine squared, that's sine squared. So we've got 2 root 2 is equal to 4 sine of theta. Now I can do a little bit of work with this. Divide both sides by 4. Sine theta is equal to the square root of 2 over 2. Well, I know that cosine would also be square root of 2 over 2, but let's just try it here. Cosine squared is equal to 1 minus sine squared. Cosine squared is equal to 1 minus square root of 2 over 2. That should be a square there. No, don't know if it got cut off. Let me see. Squared. So cosine squared is equal to 1 minus 2/4 or 1/2. So the square cosine is equal to the square root of 1/2, which is equal to the square root of 2 over 2. I probably won't have one quite that tricky on a test, but it's good to play with these just to understand. So again, if you didn't get all that, it's all written down on the answer key there.
Just add like a negative.
So this,
Yeah.
so what I did is I factored out a 16.
Okay.
So I factored out a 16 out here is just 1. Yes. What's that? Yeah. And here I factored a 16 out of the minus 16 cosine squared. So I'm left with a minus cosine squared. And from my trig identities, 1 minus cosine squared is equal to sine squared. Okay, so keep those identities handy. They will help you tremendously.
Do we have to memorize them?
No, I just said I'll give them to you, but you got to kind of know where to find them and how to use them because I mean, if you can memorize them, that's great, but I'm not gonna quiz you on memorizing them. Right. All right, so go ahead and take a look at the homework. Go ahead and turn in the in-class worksheet. The ALEKS quiz is not due for a month, and the test is not for another month, so don't sweat about that yet. The ALEKS quiz, you haven't learned everything on that yet anyway, so don't forget about them, all right? And that is where we're gonna stop for today. Yeah.